All right, let's get started. So Electric Era, I think, was to do a talk today, but they had a conflict. So they will do the talk next Thursday. Okay, so you got an email from me before. They're asking, they're looking for electric engineers and they're a local company. So they want to come and give a talk, and they will do that next week instead of today. And then if you're following the Texas grid situation, I emailed a link to the class about a seminar tomorrow that IEEE is hosting. So you're interested in finding out more information, that may be a good seminar to go to. So it should be open to the public. I just emailed the link. So you should go to that one if you're interested in finding more about what's going on there. The root cause of this crisis, electricity crisis, that is being debated fairly hotly. And I suspect we'll find more information, in the coming months. So if you're interested in this kind of system design issues, right? How do we think about a large system like Texas Grid? And I encourage you to take EE 554 offered in this coming fall. I'll be teaching that course. And in that course, we'll go into more of the system design issue. Right? How do we think about this big grid? Operation and planning and market design, things like that. Okay. So up until now, if you only taken the undergrad classes, you may not have seen that much about how to think about the system, both as from a spatial perspective as well as a temporal perspective. So if you look at the courses like 454, we do solve power flow, but it's mostly only a snapshot in time. Okay. Whereas to really manage a grid, you need to think about different time scales from years to months to days to seconds, as well as transferring power, right, from different buses. Okay, so that will be a topic covered much more in depth in classes like 554. Okay, so interest more about theory, I encourage you to take that class. Okay. If you're interested in figuring out what exactly we know right now about the Texas Grid and ERCOT, then the seminar, the link I sent out is a good one to go to tomorrow afternoon. And that's a good seminar to listen to see what people say about the current situation. Okay. Any questions there? Comments? Okay, so another thing is the homework, right? So the new homework is out. For that homework, the last question, the bonus question for the undergrad student, is sort of long. Okay, so it's a fairly practical question, but it's a long question if you do it. And several steps in it is not exactly trivial. Right? So if you're taking 551 and you're attempting that question, don't feel too bad if you don't get very far in that question. It's a non-trivial question. There's several steps associated with that question. Basically, if you take a look, that question says, how do you change the injected voltage without changing the developed power? And it's sort of a long process to get there. Okay? So that's something you can attempt to think about that problem, but again, don't feel so bad if you don't solve the entire problem. If you don't solve the full problem. All right. Okay, so then as a review, let's look at what we talked about last time for type 3 generator. Last time we basically went through the active power generation. We went through the active power flow inside the generator. So as a review for active power, we have the input power. This divides into power from the gearbox. And then this becomes injected power. And then we have some rotational loss. The developed power. Then let's divide into a slip power and the copper loss on the rotor. Together, we get the air gap power, and then we have the losses through the stator, and then the power to the grid, right? Power to the grid through the stator. Okay. So again, the thing to remember is there's two paths for power flow. Okay, we have both PS, the power delivered through the stator, as well as P slip, okay, or PR, right? So again here to remember that P slip could be negative, right? So you have a developed power, and that basically gets divided into two paths. One goes through the stator, one goes through the air gap, goes to the grid through the stator, another goes through the sort of power electronic path. Okay? There's two paths for the power to go. And for this part, for active power flow, it's just knowing where to find the equations and knowing where to find a bunch of equations we have. Okay? So this class, we're going to look at reactive power, right? As we said last time, we're interested in what happens for reactive power. So for reactive power, if you look at this, basically reactive power gets consumed by x1, x2 prime, and xm. And since in type 1 and type 2, the developed voltage and the current are 180 degrees out of phase, they cannot produce reactive power. But here, since we're injecting some voltage on the rotor side, in the secondary side, so we can have a phase offset between the current and voltage. And that leads to some reactive power production. So that so you don't have to just consume reactive power. You may be able to also provide reactive power, depending on what the injected voltage is. Okay. So if you look at reactive power, right? If you recall, basically the way the generator is connected is through a back-to-back converter, right? So we have a generator here. This is connected to the grid. We have a rotor side converter connect to the grid side converter, and this is our grid. So, right, so if you look at the power through the rotor side converter, if you look at this side of the grid, if you look at this side of the machine, then basically we have the stator, right? We have power being delivered from the stator to the grid, but we have a QS, which is a reactive power flowing out of the stator. And this can be either direction. This can be either direction, right? And because the reactive power, remember, is the imaginary part of V times I star. Okay? And this could be positive or negative once we have injected voltage, VA2. Okay? So this can go, so that's why there's a double arrow on QS. It could be negative or positive depending on exactly what the current turns out to be. All right, so if we look at more equations, okay, so let's look at basically what is QS. Okay, so let's pay more attention to what QS is. Okay. So if we look at this way, then let's look at what. Okay, so let's look at several quantities that we want to look at, right? So we have this injected voltage driving a current. So let's look at what is the total power. Let's look at what is coming out of this source. Okay, so we have a source here. Let's look at what is the complex power coming out of this source. Okay. So here what we have is we have SR, this complex power, this sort of injected complex power that's injected by the rotor side converter. There's a 3 VA 2 prime times IA2 star. Right? So this is complex power. And this divides into two parts, active and reactive part. And then we have this QRS. Okay? So this QR, right? This QR is again just due to the injected voltage, and it doesn't depend on S explicitly, right? It doesn't depend on the slip explicitly. Whereas if we look at QRS, basically, if you the reactive power that depend on the slip, then this is just the imaginary part of voltage times current. This is just this imaginary part. All right, this is this imaginary part, and we can sum the two, right? We can sum the two. If we sum the two, we get QR total, right? So this you can think of, these are the sort of total reactive power we get because we have a non-zero VA2, because we're injecting a voltage. And we're getting this much reactive power. So this QR total is QR plus QRS. This is the imaginary part of 3 VA2 over S IA2 star. All right, so this is what our QR total is, right? This comes from basically just adding the two equations, right? Adding the two equations. Again, as a reminder, we have VA2 prime over S equal to VA2 prime plus VA2 prime S1 minus S. Okay, so this is always true, right? So if you just add the two above equations, you get QR total as the imaginary part of 3 VA2 prime over S times IA2 star. And this is QR over S. So this is QR over S. This is by definition, basically. This is by definition true, right? This is by definition. That's true. Okay. So basically, what you can think of, you have QR. This is the reactive power injected by the source, by the voltage at the secondary. And this gets amplified by a factor of 1 over S. Okay, this is amplified by a factor of 1 over S, right? So remember, S is typically a number close to 0. Okay? So you divide by S, you get a number larger in magnitude. Okay, so this QR you have from the injected voltage gets amplified through S through 1 over S to the grid. Okay? Then we can look at what QS is, right? So we get a bunch of equations relating things to each other. So we have within the circuit, we have a power balance, right? We have a reactive power balance. We have QS, the grid, right? Whatever we send to the grid side, plus QR total. Okay, so these are QS is from the looking at the grid side. QR total is looking at the injected voltage. This two added together must be equal to the total amount of reactive power we dissipate in the system. And so this has to equal to Q1 plus Q2 plus Qm. Right? So this must be equal. This is all the terms associated with reactive power we have in our system. So these are equal. Then if you want, we can write this as QS plus QR over S, Q1 plus Q2 plus Qm. or QS is Q1 plus Q2 plus QM minus QR over S. So again, this could be negative or positive, depending on exactly what QR works out to be. Any questions about this? Reactive power balance? Okay, so the equations are clear, right? So the way to the calculation is clear, right? So if you know what VA2 is, you can figure out IA2, right? From the equation we've seen last class. You figure that out, you can compute QR by just using the standard VI star equation. If you know what QR is, you can figure out QR over S. Then you can, from the current, you can figure out Q1, Q2, Qm. Then together you can figure out QS. Just the once you know the current, you can compute all those numbers, right? And the tricky, sort of the unfortunate thing is we use S for stator, right? For the stator side things, but we also use S for slip. Okay, so there is, slip is called S, stator side is also called S. So that's a little bit unfortunate about the notation. So just be careful with that. Questions? Okay, so no questions. Let's look at what happens on the other side. Okay, so we have, this is our power balance, right? Remember, basically at the rotor side, at the machine side. So let's look at what happens in the grid side. Okay. Right, so in the grid side, we have this type of situation, right? We have a transformer, right? So that connects the DC to AC converter. So a transformer connects to the grid. And here we can exchange some active or reactive power with the grid. Okay, so this is the other path of power flow we have. Okay, again, the sign can go either way, can be positive or negative. So anybody remember what FCB stands for? We denote here things for FCB. Anybody remember what FCB is? You'll see this a lot in the sort of when we have wind farms, you see this acronym FCB. You might have a guess what this stands for. Anybody have a guess what F stands for? Okay, so FCB, just a reminder, it's just terminology. You can think of this as a grid if you want. But FCB is farm. Anybody have C as collection? Any guess for B? What B is? Bus, right? So FCB. Right, so what this means is just a line that all the turbines connect to. Okay, so we're gonna think there's a line running through. The turbines connect to this line. I'm gonna think of this line as sort of a bus, right, where you can connect to. That's why you see FCB. Okay, that says. Right, so that's just notation to, if you're wondering what this letter stands for. So that's our FCB, right? So then let's look at what the, what the power flow through here is. Okay, so if you look at the power flow in this setting, okay, so if you look at power flow in this setting, right? So what we have is, we have a DC voltage, right, set up in the middle. Let's go through some converter, gets to V out. So let me do this step by step, and then do this step by step. Okay, so what we have is, right, so if we just look at the power electronic path, what we have is we have set up a DC voltage. This gets converted to AC current goes to V out. We have a transformer. Gets to VFCB, right? Because this is, or you can think of this as the grid voltage we have. And this is the farm collection bus. This is a common bus where we dump power into. Okay. So we have PR, we have the QFCB, the reactive, active, and reactive power. Okay. So the way we're going to look at this from a circuit perspective is let's look at all of these and think of this after the converter, after the transformer. Basically, just some voltage VL prime with some angle delta. Okay. Right, so this is just some voltage. So if you look at this circuit from the farm collections point of view, from the grid's perspective, you see a voltage with some angle. Okay, so this angle could be controlled by the converter, but for now, just think of some angle. Then our transformer gets modeled with some reactance, right? This is the series reactance we have in our transformer. And then we get to the grid side, the FCB side. Okay, so this is our circuit model, right? And we have some current flowing through this reactance. Okay. So I have, right? So what we care about is how much power, right? So how much power do I get here? Well, okay, so let's say this reactance has X, right? Has a angle X. Then what we have is that we care about how much power we have here, active and reactive. Okay. So to figure out the power, what we can do is we'll still use voltage times current, right? Voltage times current. Okay. But what we take is we'll take VFCB as the reference, as the angle reference, that's a zero angle reference. Okay. And then the current, so this I, complex current, is just V out angle delta minus VFCB divided by JX. Right. This is just current flow. This is V out, expanding this, cosine delta plus J sine delta minus VFCB over JX. You simply divide and read out the real and imaginary parts. Just divide and read this out. What you get this is V out prime X sine delta plus J VFCB minus V out cosine delta over X. This is our current, right? Then what we can do is we have the complex power given here. This is just VFCB I star. Okay, so you can compute the current this way if you know delta. Then this is PR plus JQ FCB. However much reactive power we deliver or consume from the grid. Okay, any questions about this computation? Questions about this? Right, so this requires us to know the angle delta, which is in some sense a controllable variable by the converter, right? So this converter is converting from DC to AC. So it has an angle can set pretty much arbitrarily. Okay, so we should think of this angle as you set this angle to achieve some objective. But if you know the angle, then computing for current and power is not very difficult. You compute, if we are given the angle, we can compute the current and the power flow. So knowing the angle is something like this. So that's the same thing we did. Then you can just multiply V with I star. Okay, there's just a straightforward multiplication with V plus I star. Then this is, if you just multiply this out, you get the familiar relationship we have right? This is active power, something over the reactance x times sine of the angle, and this is reactive power depending on the cosine of the angle. So this is what we have. Any questions about this power calculations? Okay, so it may seem, again, in this section of the class, there's a bunch of formulas, which is true. There's just formulas flying around all the time. But as useful to know where the formula come from, which formula applies to which part. Okay, so distinct parts of our type 3 has different formulas associated with it. And these are the formula associated with the grid side converter and the farm collection point. Okay, this is just where the formula is. All right, so then we have these formulas, and these are the power flow. Okay, so now we can look at, right, so we have active power and reactive power. We don't care about the active power so much. Okay, we're gonna care less about active power, right? Because again, active power mostly flows through the stator side, right? Mostly flows from stator to the farm collection point, to the grid. And delta is not terribly large in practice, but we care more about the reactive power part. Okay, so let's look at this reactive power, what happens. Okay. So you look at reactive power, basically by changing this angle, okay, by changing the angle and the voltage as the power electronics, I can have positive, negative, zero reactive power delivered to the grid. Okay. And whether you want this to be positive, negative, or zero, depending on exactly the grid condition. But these are the control variables we have. Okay, so the VL prime is something we can control using a converter. Delta is something we can control using the converter. So these are the degrees of freedom we have. Okay, degrees of freedom we have to shape reactive power flow the way we want to do. Okay. Questions about this? Okay, so this is reactive power. So let's do an example to see how we use this. Right, so again, the key part about type 3 is when you look at the question, just the key actually identifying which equation do I use. There's a number of equations, which ones do I use? Right, how do we think about the power balance in the system? Let's do one example. Okay, so let's say, okay, so let's do one example. So let's say I have a Dfig system. Okay, let's say I have a system and has 6 poles, 60 Hertz, Y connected, so common setup. Then I have all these kind of parameters. Then without injection, let's compute the developed power at a certain speed. We increase the speed, but we want to find the voltage that maintains the developed power constant. Okay? We want to maintain the developed power constant. Right? We want to find this voltage. And to finding this voltage normally consists of finding both the magnitude and phase. Okay, so finding that can be tricky. Finding both magnitude and phase can be tricky because you're dealing with a complex variable. So for this question, we're going to make it slightly easier, and we're going to give you the phase. Okay. So the question is, I have a machine, I'm happy with developed power. Suddenly, I have the machine speeds up, maybe because higher wind, but still I want to keep the developed power constant. So I don't need more power on my system, I want to keep it constant. Okay. So then the way I do it make this constant is I inject some voltage in the rotor. Normally, you need to think both about the magnitude and the angle of this injected voltage. You need to control both. So here, we're going to make it a little bit simpler and just look at the injected magnitude. I'm going to say the injected angle is 180 degrees out of phase. Okay, so let's look at how we solve this problem. So is the problem clear? Okay, so this happens a lot. This is actually sort of the real-time feedback control you do. Okay, when increases, you figure out do I want more power or not? And then how much more power do I want? And then you bias your injector voltage. And you bias your injector voltage to achieve that. Okay. All right, so the first part is simple, right? We're gonna figure out what the developed power is. And from this developed power, we're gonna look at what number should we keep it to be constant. Okay. So we have xm. So here we're gonna say that xm is very large than everything else we have in the xm is much larger than x1. Okay, so here we're basically going to think of the equivalent circuit as something like this. Okay, we're going to ignore the stator part of things. Okay, and this is without injector voltage. So this is just a short in our case. Okay. All right, so if you do a homework on the exam, I'll exactly say what to ignore, what not to ignore. But for this example, this is a case where if the xm is so much larger than x1 and x2, 50 times larger, then you can safely ignore it. It won't change much in your calculations. So let's look at our slip. This is 1200 minus 1230, 100. So this is minus 0.925. Okay. My developed resistance, this is R2 prime S1 minus S. Okay, so this is negative 0.41 ohms. And we can compute the current going through, the magnitude of the current going through here as VA1 square root of R2 over S squared plus, so this is X equivalent, X1 plus X2 prime squared. Okay, so this is our current through the system. Then my developed power is minus 3 RD A2 prime squared. So we have done this for calculation many times. You get 976 kilowatt. Okay. So this is without injector voltage. We get developed power of 976 kilowatts. And our goal is to say with the injector voltage, let's keep this constant. Okay, so let's try to keep this constant, right? Okay, so now we're going to inject some voltage here. So if we inject the voltage, so we're still going to move the shunt in front. But now we're going to have a VA2 prime. Okay, let's inject some voltage into the system. And the slip here changes, right? So our slip changes. So the slip, since we're operating at a new speed, the slip gets larger, or I guess more negative. So a bit larger. Then our developed resistance, we can compute this again, R2 prime, S1 minus S. This is minus 2, 1 ohms. Okay, so our slip is a bit larger. And then our current is given, since we have VA2 now, minus VA2 prime over S minus VA1 R2 over S squared plus X1 plus X2 squared. Right. So where does this minus VA2S come from? Where does the minus sign come from in this equation? Right, is this comes from 180 degrees out of phase, right? So recall, this numerator is normally VA2 as a complex voltage minus VA1, right? Normally we have to look at the complex voltage. But to make things simple and not think about complex numbers, right? Just think about magnitude. What we do is with no VA2 as 180 degrees out of phase to VA1. Okay, all right, this is 180 degrees out of phase. So VA2 as a complex number equals minus VA2, right? Okay. So we can, the angle, since the angle is null, and the angle is specifically picked to be 180 degrees out of phase to not introduce a imaginary part. Okay, this is sort of chosen to make the problem numerically nice. We have a current set up like this. Okay, and the rest is to solve for the value of VA2, right? Such that the developed power stays constant. Okay. Okay. Right, so this is our equation. Okay. So right, so let's go on with this equation. Okay, so let's say this is the I2 equation. Okay. So at the end of the day, what do I want, right? What I want is, I want the PD, I want this to stay constant. Okay, so let's now plug in, right? Let's plug in what the PD equation is. Okay, so we can plug this into our new PD equation. So this developed power, remember, has 3 RD IA2 prime squared. Okay, so this is always there, the power, and then plus 3 VA2 prime over S. So if you want to write out the full equation with the complex numbers, S1 minus S, IA2 star. But here, since we pick all the angles to be nice, what we get is just minus 3 RD, IA2 IA2 prime squared minus 3 VA2. Just substitute this into there, minus 3 VA2 prime S one minus S times this IA2. So we're not going to start this, we're going to simply multiply by IA2. All right, so this is our equation. And now we want to equate this. We want to equate this to what we had before. I want to equate this to the PD we had before. So I want to equate this one to the PD we figured out in the first part as 976 kilowatt. Okay. So our goal is to solve for VA2 prime. Okay. Our goal is to solve for VA2 prime. Right? Any questions up to this point? Okay. So our goal is we get this equation. We can write out the developed power equation with VA2 prime. Right? We know what we want the value to be. We want it to be 976 kilowatts. So we solve this. Okay. So what type of equation is this? If you look at it as a linear, quadratic, what kind of equation do we have here? We look at this equation. Right, so this quadratic equation, right? We are squaring the current. Current depends on the voltage, VA2. So we have a IA squared, we have a VA2 times IA2. Okay, so all this, so this is a quadratic in VA2 prime. Right, so this is nice because again, we don't have an angle, right? So the angle is predetermined. We're only going to solve the voltage. Okay, we're only going to solve the voltage. So this quadratic equation in terms of the voltage, you can collect terms and reduce it if you want. Then we get VA2 prime equals to 26.9 volts. Okay, we get this number. We got this is our VA2 prime. And if we want, here we have a transformer, right, with a turns ratio of 5. So if you want this as in not reference to the stator side, then that's just VA2 prime times 1/5. This is 5.38 volts. Okay. So in absolute terms, you basically inject a voltage, fairly small voltage, about 5.4 volts. And you can, when there's a large speed change, you can still keep the rotor. You can still keep the developed power the same. Okay, so this is the example of developed power control. Any question with this? Okay, so normally this VA2 will come out to be small number, right? We're not looking for a voltage on par with the grid voltage. We're normally not looking for this kind of numbers, right? What we're looking for is for small numbers you can inject that will keep the small numbers, so I'll keep the operation steady. Okay. And this kind of small numbers work because we're dividing by S. Okay, S, right? So S is something like 0.05 or 0.025. So you are getting amplified. Right? So this, once you divide by S, it's a reasonably large number. But in terms of absolute numbers, it's not terribly large. So roughly 5 to volts, around that range. Okay, so this is part of the turbine. This is in the feedback, right? You basically have a sensor measuring the turbine speed. Then this feeds back to a controller. That controller determines what VA2 prime is. Okay. So in this question, we did not look at reactive power. We basically said, injecting this voltage with the angle 180 degrees out of phase creates some reactive power, right? The changes reactive power consumption. But we did not worry too much about that. Okay. We're basically saying we want the active power to be constant. The reactive power, we can deal with it, and deal with the reactive power. Okay. So in the homework question, last question in the homework, asks for both reactive and active power. So the voltage you solve is no longer just a real number. You need to solve for an angle as well. Okay, so that's a more realistic operation. In practice, you never just care about the active power. You may want to keep, for example, the active power and reactive power constant by setting an angle as well as a magnitude. That's quite involved. It's not. Yeah, so that's a sort of longer calculation. That's a longer calculation. Okay, so you can explore that in the homework, but it's a sort of non-trivial question. Okay, so you don't have to feel that you have to solve the entire problem too. Okay. So now it's a good time to take a break. We'll come back at 1:28. We'll talk about things like stability and protection of type 3. Okay, so let's take a break until 1:28 p.m. Okay, so let's get started again. All right, so here now we're going to look at the control of type 3 or Dfig generators. All right, so by control is again, we mean we want to look at the stability information or the range of operations you can have when you are running this kind of turbine. So if you look at control, what we have is basically control comes down to a balancing, right, of two things. One is the mechanical power or mechanical torque you get from the gearbox. Another is how much energy you send out, right? You send out to the grid, or the electric torque the generator is converting to electric power. So this is the basic balancing equation. Okay, so this is the difference in torque. Right, so the difference in torque depends on the derivative of the speed of the angular speed, right? So that's just Newton's second law, right? This is F equals ma, basically. Okay, so for in a rotating system, we have torque, right? And the difference in torque is the inertia constant h times the changing speed, changing the rotation speed, which is acceleration. Right? So that's our basic equation. Okay. So there's different ways we can have the turbine operate, right? We may insist on something like a constant speed operation. So we can insist on things like constant speed operation. Okay. A constant speed operation basically says that I want this omega-2 to not change. Okay, so I want the speed of my turbine to be constant. Right? So how do you maintain speed? Well, to maintain speed, again, Tm minus Td equals to 2h d omega-2 dt. Okay, so constant speed means omega-2 as a constant. That means d omega dt is 0. Right, and so the idea is if you want the turbine to be within constant speed, what you can do is you shift Td to track Tm. Okay, so the injector voltage, right? So this Tm, this depends on what? Okay, so this is depend on nature, right? It's a random number. It changes time to time. This depends on VA2. Okay, so the way this works is you want to always track Tm. Tm changes as wind changes, as how much power torque you get from the gearbox. So you keep changing your injector voltage, right, to match Tm, such that you don't have a changing speed. Right, so this is basically one mode of operations. Right, again, VA2, since VA2 is done through a electronics, right, through solid state electronics, that's fairly fast. Okay, so you can track the changing Tm fairly, the speed is not an issue, or the speed of response is not an issue. You can track Tm. Yeah, you can keep the rotor speed constant if you want. Right, so there's one mode of operations. There's another mode of operation. You can think of variable speed. You can think of variable speed. Right, so variable speed means following, right? So variable speed means, again, Tm minus Td equals dd omega-2 dt, okay? So what variable speed says is, I want to change my speed, maybe to maximize Cp, right? So normally variable speed is, let me induce a change in the speed to track Cp. And in addition to pitching the blade, what you can do at a faster time scale is use VA2 to change Td. Okay? Think of Tm being constant, but Td is changing because I'm changing VA2. This induces a difference, right? So Tm minus Td is no longer 0. This will cause omega-2 to change. It will cause the speed to change. And then we can maximize Cp this way. Right? I can maximize TSR. this way. Okay, I can sort of adjust the, so I can move the speed to a speed, let's say maximize CP. Now adjust my TD again to make sure I operate at this sort of new speed, this sort of more efficient speed. I can track the maximum power operating point. Okay, and this is a way to, right, we want to do this, but maybe, you know, this may be better than mechanically changing the speed or power. It's because solid state things are just faster. Right? It's faster. You can implement different control laws. You know, you can change your TD. You can say do optimal control problem of how to get there in the fastest speed or use the least action, things like this. And so this gives you quite a bit of flexibility for this type of turbine control. Right? So you can either do fixed speed or variable speed, okay, from type 3. Any questions about these modes of different operational modes? Okay, so when you design the turbine and when you design software, there's actually a lot of software associated with the turbine. Okay, you need to build the turbine, but the control feedback loop is actually quite complicated. There's a lot of feedback control going on. And these sort of different operating modes you can select. So it's more than nowadays, it's a lot more than just build, you know, physically constructing the turbine. As you have to put all this sort of control loop around it to make sure it works. So this control loops we have. Right? So this is tracking speed. The next thing is, of course, always protection. Right? So we have this turbine. How do we make sure that you don't burn something out, right? You don't break something. So protection is an important issue. And protection because, right, so we have, remember the solid state, right? We have this converter path where power can flow. We have current basically flowing this path. Well, these are converters, but they're not, right? They have some maximum rating they can operate at. Okay, so what you need to make sure that you satisfy these limits. Okay, so make sure you satisfy the voltage and current limit, right? So just because you have the solid state power electronic path doesn't mean you can dump arbitrary power, right? So type 3, the main path that active power flows is still through the rotor, through the air gap to the stator. Okay, it's not that, you know, I can ignore that direction and flow everything through my converters. That's not the case for type 2. Okay, these converters normally, you know, cannot deliver majority of the rated power. That's our limits there. Right, so if you operate, you know, if you're dumping a lot of currents or heat issues, right, you have to get rid of the heat somehow. Okay. And the heat actually, you know, you can heat it quite a bit, actually, because there's so much current flowing there. Heating can be an issue. It's not dissipating the heat is not trivial. Right, so depending on where your turbine is installed, you have to worry about how much heat can dissipate through this turbine. Okay, that translates to how much current can it tolerate, right? So how much, there's kind of limits. Okay. Right, so then if you look at more electric quantities, things like current and voltage, what you're looking at is, you know, we have things like surge current, right? So if the current, what is the maximum current I can tolerate? Okay, so this is not a steady state, but let's say something happens, you got a big sort of a step or delta function, almost like a current. And what is the maximum you can, what is the maximum you can tolerate, right? Then we need to look at his, what is the maximum rate of change of current, right? So if the current changes too fast, we run into issues, right? We cannot, again, you know, so sending a step function may not be that trivial through this because you have inductors and capacitors. Okay, they oppose to sudden changing current and voltage. So we care about maximum dI/dt and maximum dV/dt. Okay, we care about this kind of limits. Any questions about this for the limits we care about? Right. So again, just because you have electronics path, we still need to make sure that we don't overload this path. You don't overheat it. You don't change the voltage too quickly or the current too quickly on this path. So that's where the sort of the building protection equipment goes in. All right, so there's two again. So if you look at protections, there are two main types of protection. One is electrical protection. This is really for to balance current, to protect against overcurrent, over voltage. And this is really to say, because we have circuits here, right? It just maybe I got to fall somewhere in the circuit. Maybe that creates a lot of current. Right? So how do I protect against that? The electromechanical protection is more familiar to us. This is basically goes back to, again, what if I'm providing more mechanical power than the electrical power that can be delivered to the grid? Okay, so electrical protection is the gearbox mechanical side is fine. Adjusting all my circuitry, something is causing a current surge. Whereas electromechanical protection is, I have too much wind, basically. I have too much wind, I can't get rid of this power. Now what do I do? How do I design protection this? Okay, so this is the two main types of protections we have. Right, so electric protection, there are events, again, basically that cause a surge in signal winding on the machine. Right, so if something gets coupled to something else, you may see a current surge. So if the rotor is, so these are all wires coming in out of the rotor, so you may see a current surge that way. And the main goal is to not short out the rotor side converter. Okay, you don't want to damage that. Okay, you don't want to damage that component, right? You want to protect against that current surge. Okay. Our electromechanical is, we have seen this many times, right? With the power, right? I cannot, on the stator side, I cannot deliver that much power, maybe because of a fault on the grid side. But then my wind turbine is still going, right? My wind turbine, my blades are still spinning. I'm still generating a lot of power in the gearbox, right? So how do you dump this power? Okay, how do you quickly dump this power as a protection issue? Okay. So let's look at the electrical protection first. Okay, let's look at electrical protection. And the names for this part is quite sort of straightforward, quite intuitive. There's a thing called crowbar, and a thing called chopper. And so this sort of mean exactly what you think it means. Okay, so a crowbar is basically saying that I'm still going to have resistors hanging out here that will burn out power, basically. So remember, I have my power. I have a path going from the rotor to the converter side, going to the converter side. If I need to get rid of excess power, what I can do is I can add some resistors in parallel, divert some current, just that the current goes to resistors and reduce the power that the rotor side converter can handle. Okay, so this is called a crowbar system because this is as if you have a crowbar, right, on the rotor side converter. Right. Any questions about this? So all this are just adding resistors to burn power away. And the question is, so where you add resistors? So here in crowbar system, we'll add it to the rotor side. Right. Okay, so this is our crowbar side system. So the main issue to think about in this crowbar is you don't want to falsely trigger the protection system. Okay, so you don't want to falsely trigger it. Because what we have is I have some voltage, right? I'm setting up some voltage on this side. This voltage induces a current flow on both sides. Okay, induces a current flow. Okay. You want basically such that you don't want the DC component to show up on the other side of the converter. Okay, so you don't want to. No, you basically want to set the value for this resistance such that they're not very large. Okay, so you don't want the resistors to pull too much power, right? You don't want to sort of falsely trigger the system. Okay, so you cannot arbitrarily set the value of the resistors because you're worried that this resistors, when there's a lot of current running through them, you're pulling current from the wrong direction. You worry about that, right? You don't want them to pull so much current that the voltage drops below VDC. You don't want the voltage drop to be larger than VDC. Okay, so you want to make sure that the current goes the right way, right? You don't want to pull reverse current out of your converter just to feed the just to dump power through that way. Okay, so you want to engineer in such a way that the resistance is in a correct range. Okay, in a correct range. Okay. So then the crowbar is basically just a current divider. Okay, so this is just a current divider. So you activate the system when you're getting too much current going through it, and this crowbar acts like a current divider. Okay, so what this does is, right? So what this does is this basically is very similar to the dynamic braking we have seen, right? This is very similar to the dynamic braking we have seen before in an induction machine. Because this is just as if there's too much current, I need the current to go somewhere else. And this is dumped through this resistors. I'm dumping current through this resistors. So it's quite similar to the dynamic braking system. It's basically, if you remember the calculation we did earlier, it's basically we're going to activate dynamic braking for a, let's say, half a second, or tens or hundreds of milliseconds. Right, so this is saying if there is a fault, let's activate this system. Let's just dump power through this resistors. And normally they're designed to activate for about 2 seconds or so. And if you activate for 2 seconds, the hope is by that time the fault will be cleared. And the hope is if you have a fault, and the fault will be cleared after 2 seconds, and you can go back to normal operations. So a question for us, right, to think about, and this goes to Parsons protection, is why would a fault be cleared after 2 seconds? Right. So why is there's a lot of protection in the power system engineer, such that the dynamic braking or other things only for a short time, 1 or 2 seconds. Then you hope the system goes back to normal. Okay, so why can we hope the system go back to normal? Right? Why isn't that the way? There's a fault. Let's just open the breakers and do things like that. Why is it that we have this sort of 1 second, 2 second, buffer time, and you hope the system will recover after this fault? Right, so why is protection? Anybody know protection? Why do we engineer the system to have this sort of buffer time? Why not just say, if there's a fault, just open the breaker. Let's not worry about. Anybody have idea? So why do we engineer this sort of buffer times into the system? Okay, so normally the reason we engineer this kind of buffer time as it's hard to tell whether the fault on the system is a transient behavior or is it due to some permanent behavior, right? So let's say you're operating the system and you have a thunderstorm. So lighting, hits somewhere close to your line, right? What that shows up is that may show up as a current surge in your line, but that's a very transient behavior. Okay, so if your protection is such that for any current surge, I'm just going to open up all the breakers I have, you may be overly conservative. You may be overly conservative if you just do it that way. So the breakers are designed basically to open and close, right? So the breaker working in such a way such that, let's say you have lightning striking somewhere, you have a current surge on this line. Then what you do is the breaker on this line will open because you do have too much current. So you open for safety. But since you don't know whether this is a transient or permanent behavior, right? Then you try to close again after say 1 second or so. Right? You open, you close again. If it is really a transient behavior, really is a lightning striking a line, then by the time you close again, things will be fine. You will have no current surge anymore. It'll be a sort of normal operation. Okay? So then the way that design, since the protection system can only measure local information, so a current surge is not clear whether how long this thing will last, right? Is it because the lightning strike? Is it because some tree hit a line? Is it because some other problem, problem in other part of the system? So you open, then you close after a second. Hopefully, this is a transient behavior. It has gone away. Okay, yeah, then you close for a second, right? So you open once, you try to close, and then basically there's a design sequence of how you open and close, and you only permanently open after a few unsuccessful attempts for closing. Okay, so you open and close, open and close. So that's why sometimes even we will experience for flickering. Right? So sometimes at home, you may experience your power going out for a second or so. This is because your protection system opened and closed. Okay, so you may lose power for a few seconds, but then that may be because of transient behavior. So once you close again, everything's normal. Okay, so this kind of resistance is really to say, can I live through that, 1 or 2 seconds of transience? All right, you want to live through that, and hopefully things are clear, you can reconnect. If not, then you permanently open the breaker. Okay, so that's what these crowbar systems are designed to do. You only operate, you provide some buffer to the system. Okay? And quite a number of faults we have in our system are transient faults. Like they're not, it's not like a line just permanently goes out commission, right? Maybe, there's a lightning strike, there's an animal who got there, that briefly shorted the line, the path like that. Okay, so that's the, right? So we have this kind of protection. Okay, so it sort of makes sense to design systems that only works for 1 or 2 seconds. Okay, so none of these are designed to dump power for let's say half an hour, but they're designed to dump power over a very short amount of time. Okay, so that's a crowbar system, right? That's our crowbar system. Okay. So if you have the crowbar system, well, the crowbar system is basically if the crowbar system activates, then you're still getting some power flow from the grid side. So there's an issue of active power and reactive power being worked out. Right? So the crowbar system is not trivial. This is not trivial, right? So because you're not actually disconnecting, right? You dump power through this way, but when your turbine may be operating to be getting reactive power from the converter. So if you operate your crowbar system, you may be no longer getting reactive power. So this reactive power has to flow from the grid, and this can cause voltage issues. The protection on a turbine is actually quite complicated. Okay, there's a bunch of standards you have to follow, and then you have to work out sort of the different protection schemes to satisfy the requirement of a bunch of standards. Okay, so it's not a trivial thing to design protection. All right. Okay, so this is a protection system we have, right? So again, the value is you need to choose it very carefully, right? So the problem with the crowbar system is it's sort of hard to choose the values. You want to do many things. You want to dump power, but you don't want to, but you still want some reactive power flow. So this puts a very limited range on the numbers you can choose for the crowbar system. It puts a sort of very limited range on that. So we'll do some calculations, but next time. But turns out just hard to choose these values. So next time we'll look at the chopper system, which makes things slightly easier. Okay, which makes things slightly easier. Turns out crowbar is a hard system to use. It's hard system to design. Okay, so I have to go in 4 minutes because I need to speak with a seminar speaker this afternoon. So I need to go in 2 minutes. So let's end the class here today. Right? So end the class here today. As a reminder, the homework is out. Right? So for this week, the homework may be long. Right? So type 3 is very famous for giving long problems. That's not hard, but tedious. So you do want to take a look, right? You may not want, wait until say next Wednesday morning starting homework. Okay, so take a look at homework. It could appear long, right? So then otherwise, I'll see you next Tuesday. Thanks, guys.